Last time, we discussed this idea of the geometric realization, and we looked at the mapping that goes from graphs into topological spaces. That is, we could take this graph, which was just this combinatorial object, finite sets and finite sets of vertices and finite sets of pairs of those vertices, and turn it into this geometric object, which included these line segments and points and really an infinite number of points, right, along a line segment, so even for one edge. And it lived in some high-dimensional space. And I hinted, and actually I didn't just hint, I told you directly that the goal of this was to help us to then think about and reason about drawings of the graph when we draw them on paper. And today we're going to actually get there and do that. So, the topic today, drawings and embeddings. There are examples of graphs. Like here's a drawing of a graph. And I do funny things, right? When I draw these graphs is I put a little space around the vertices just so it's clear where a vertex is. But you should always interpret that as, being connected. And I also do these other things like, look at this. I've got a little gap here. You notice so that you can see that one edge sort of goes over or under another edge. And so you don't get confused and think that there's a vertex there. We do these kind of drawing tricks. These are not the kind of aspects of a drawing that we care about, right? They're just help us to communicate. But this is a funny graph. If you were to kind of try to work through it, you might eventually see that this is K33. It's a complete bipartite graph where three vertices on each set. I can color it here. There's 1, 2, 3, and 1, 2, 3. There's my two coloring, so it's bipartite, and you see that each of the red vertices is connected to each of the blue vertices and vice versa. Complete bipartite graph. This graph, if you try to draw it without any crossings, you would, at least if you try to draw it on a piece of paper, you'll get stumped. You can draw it on a coffee cup, which is a fun problem. But for now, if you're just drawing on paper, you get stuck. And you just can't do it. There just doesn't exist a way to do it. And we want to formalize this notion of the existence of non-crossing drawings in a clear way and express it and understand it in terms of graph invariance and in terms of the geometric realization. Right. So another example that we talked about, things like K4, you notice that, like in this case, I might do this drawing, and as I get to here, and I got to get the edge from here to here, I might draw like this. And so now I have edges with curves. And that's another idea we're going to have to think about. Like what happens if I allow curves in my edges as opposed to just the straight line segments we saw in the geometric realization? Does anything interesting or different happen? Do I get new kinds of graphs that maybe require some curves? We're going to study that question. But in general, the whole point here is to take this geometric realization of a graph, which lives in Rn, and we're going to try to map it down into, for now, the plane. But you can think of other spaces we map it down into. All right, so curves are an example of something that you see a lot, maybe in math, right? Simple examples of, a function from an interval into the plane. But you can think of the curve two different ways. Like oftentimes we think of this curve as a set of points in the plane. And it's true, it kind of defines a set of points in the plane. But the function is more than that, because the function gives us a parameterization, right? Like here's gamma of 0 is the start, gamma of 1 is the end, right? At some point in the middle I've got gamma of t. And in fact, you'll see that because the function of this curve crosses itself, right, then it's not injective. It's still continuous. It's still a continuous function from this interval into the plane. So why is this important for graph drawing? Well, if we're going to draw edges in the plane, we are going to draw them as continuous curves. So that's how we want to think of this this parameterized curve. And this is a theme you'll see in this course and actually throughout mathematics, is that you can also often find this confusion between thinking about the object as it is, which is usually as a function, and its image right, in the space. And we saw this before, right? What was our good example of a case where we should think about the function and not the image? I think examples would be things like sometimes subgraphs. It's handy to think about the homomorphism that maps the subgraph into the graph. So if it just has a subgraph isomorphic to a particular graph, right, there's some homomorphism, some injective homomorphism from one into the other, right? That homomorphism is sometimes more interesting than just the image. We did this with cycles and paths as a special case, or walks in a graph. All right, so we're going to draw the graph, and so the drawing of the graph is going to have vertices as points, and the edges are going to be curves like this. And what's kind of nice is that the geometric realization actually already has these two properties, right? That's exactly how we defined it. The curves happen to be a special case of these curves. There weren't curves in the plane, but there were curves in Rn. And they were line segments, right? Which is perhaps the simplest kind of curve you can write. So what we have then is that the geometric realization of G is a kind of drawing. I haven't given the technical definition yet, but you can think of that as a drawing in Rn, and now we're going to generalize that just a little bit. Okay. So formally, a drawing of the graph G is a continuous map from its geometric realization into usually some Euclidean space. I'm just going to call it RD here, some dimension. And in this case where, say, d equals 2, which is maybe our most common case, then we would call it a planar drawing. Okay. So similarly, or kind of building on drawings, an embedding is an injective drawing. And remember, injectivity means that you don't have more than one point mapping to the same point. Right, so this gives us, right, no crossings. Right, I can't have, for instance, two vertices placed at the same point. I can't have an edge crossing itself or crossing any other edge. So in pictures here, I might take this up in 3 dimensions. I might have this geometric, actually technically 4 dimensions, but you can draw it in 3 dimensions as well. The geometric realization of K4. And you can think about an embedding of this graph in the plane. And maybe I just embed it, straight down, like a linear embedding. Right, then I'll get, this is a continuous map. But it's not injective, it does have a crossing. And I might have another embedding, say over here, which does not have a crossing. And this one might also be linear, in fact. Like another linear map, keeping straight lines straight. But you can have other ones which are not so linear, but still continuous. So a nice third case might be something even that looks really weird. This is also K4. I'll just highlight where I put the vertices because you can lose them in all the squiggles. This is all, as long as this is continuous, then this is also a drawing of K4, and this one is also an embedding, right? So these two are embeddings. This one's a drawing, but not an embedding. All right, now here's a nice exercise to get us warmed up, I think, thinking about drawings and embeddings. It's an important fact, right? Every graph can be embedded in R3, right? So if I were to just try to take a mapping from the graph into 3 dimensions, I can always do it without crossings, right? The embedding means injective, don't forget, so that means I have no crossings. And the idea is pretty simple. In fact, I think I would hazard to say that if you thought about this a little bit, you might come up with at least a strong belief that this is true. Because if you take your vertices as points in R3, And you just need to be able to connect every pair of vertices with some path through three-dimensional space. It doesn't seem like just having edges can block you from getting from, say, a vertex U to a vertex V. Like, it seems like if you view this an embedding of a graph as some tangle, there's always some path that I can squeeze through the tangle. And we can make that concrete, but in fact you can make it even stronger by showing the following thing, is that you can pick the vertices, which are or where the vertices will go in the embedding. So we're just picking some points, P0, P1, up to Pn minus 1. So I'm going to pick these as points in R3. And I'm going to pick them so that no 4 points are coplanar. So no 4 points are coplanar. Now you can do this just by perturbing them randomly. If you were to randomly perturb them by any set of n points by some small amount, then you're not going to end up with 4 points on a plane, right? Because any 3 points define a plane, and so the 4th point by any small perturbation is going to generally move off that plane and will no longer be coplanar. So you can do this, and once you believe you can do this, now you can get the following embedding. Right? It's going to be the linear map. Let's call it M. I'm going to represent it by a matrix, and it's going to be a mapping from Rn down into R3, such that the following happens, right? So the linear map applied to the standard ith standard basis vector is just going to be equal to Pi. This in fact tells you what how to write M. M's will just have columns equal to the coordinates of the points, right? Because it's going to be a 3 by n matrix, and each column is just going to be one of the points, right? The ith column will be the ith point. So if I just write out that matrix, it gives me a linear map, and so this is a continuous function from Rn to R3, and so if I restrict it to the geometric realization, it's also going to be continuous, and we just have to check really that it's also injective, right? So why is it injective? Well, a crossing, that is some point where it was not injective, would be 4 points, right? Because there's going to be 2 edges, and now the edges are going to map to straight lines because this is a linear map. So it would be these 2 edges, let's call them A, B, and C, D in the graph, such that when I embed them, the line segment PA, PB intersects with the line segment PC, PD, right? So AB is going to map to this line segment, CD is going to map to this line segment, and if their intersection is non-empty, then that means they cross. That's what it means to cross. So, but this would imply, right, if you have 2 line segments that cross, this implies that these points, PA, PB, PC, and PD, that those points are all coplanar, which we explicitly chose them not to be, right? So that's a contradiction. So this implies that really there aren't any crossings, and that this mapping, this linear mapping we got from just mapping the vertices to these points is in fact an embedding. Right? So you can get an embedding without trying too hard if you go into R3. But on the other hand, not all graphs can be embedded into the plane. In fact, a special case of a graph that can is called a planar graph, right? So a graph G is planar if there exists an embedding of that graph into R2. Now, here are 2, these are really the canonical examples of what we would call non-planar graphs. These are graphs that cannot be embedded in the plane. There is no way to find a continuous embedding, a continuous map from the geometric realization of this. This graph is K5, and this one is K33, which we saw at the beginning of this video. There's no way to draw these without crossing. If you try to draw it with as few crossings as possible, you get what I think are much better drawings of these two graphs, although usually when people draw them, they draw them just like this, right? They draw the pentagon with a star in it, or they draw 2 rows of 3 with all these, all the edges going across. But really, I think this one is much nicer because you can draw it with just one crossing. And this is the one we started with for K33. Right? The 6 vertices are like this. They make a square here. And then there's just this one crossing. It feels like it has just this one twist that happened. If you feel like if you could just untwist it, you would create a crossing on the top. And somehow there's just no way to get rid of the one crossing. It also kind of highlights the sense in which is minimal. You know, if you were to remove one of these edges, you'd be able to draw it without a crossing. K5, similarly, you can draw it like this. You could draw it like a triangle, and it also looks like it has a kind of twist right here. This one. Okay, if you could just, it seems like if you could just untwist right here, this crossing, you could get rid of the, you could draw it without crossings, but you can't, right? There's just no way to rearrange these points or rearrange how you drew the edges to make it an embedding in the plane. Okay, so these are the two kind of canonical examples that we'll always go back to. And actually soon we'll see that these in fact define what it means to be nonplanar, that every nonplanar graph is going to have one of these two graphs hidden inside it, and we'll talk about 2 different ways to hide a graph inside another graph. And so these are really, really important examples. Okay, but you can at least, before we get to the technical proofs of that fact, you can at least convince yourself by trying a bunch of times that it seems at least believable that you cannot embed these 2 graphs. So they do exist, these non-planar graphs exist, and so it's an interesting distinction to talk about which graphs you actually can draw in the plane. And we've seen a bunch of examples. In fact, a lot of the graphs we've already drawn are planar so that we can draw them in the plane without crossings. All right, but here's an interesting fact about embeddings that we want to kind of highlight, right? That if you do have an embedding of the graph, injective continuous map from its geometric realization, then the image of that map, right, is going to be a subset of that Euclidean space. Right? It's defined to be f of the geometric realization of G. Remember that we use this notation when I take a function applied to a whole set, I mean all the points you can get to. It's the same thing as the image. That image is in fact homeomorphic to the geometric realization of the graph we started with. If you want to prove this, we're going to use a kind of a common technique, and I can't give you the full proof here because some of it's going to depend on some facts from topology, but they're not too surprising ones, is that I'm going to take this function f, and I'm going to call this the co-restriction, because I'm going to take the codomain to be just the image. All right, so technically f mapped it, say, all the way into, if this is a planar embedding, then it's a mapping into R2, but we restrict it to just its the codomain to the image, and that kind of forces this to be a surjective function. If it's an embedding, then it's injective, it's surjective, and then since it's an embedding, it's also continuous. Okay, so just by all the definitions here, f prime is injective, surjective, and continuous. Now, you might hope that that automatically means that it's a homeomorphism, and in fact it does, but I have to, it's required that I highlight the fact that this is a not obvious fact, and it's not true in other kinds of, in all topological spaces. So really we're using the fact, this is a classic fact, right, that there's an inverse to this f prime is also continuous. This is a extension or generalization of the inverse function theorem that you may have learned in calculus in high school or college. And it really is using properties of Rn in this case. We're really relying on the fact that this Euclidean space that we're mapping into is what's called a Hausdorff space. I won't go into the definition here, but the geometric realization is in topology what we call a compact set, and functions, continuous bijections from a compact set into a Hausdorff space always have this continuous inverse. So if you know a little topology, you'll recognize this fact because it's a basic fact in point set topology. And if not, you can look it up, or if you don't care, you can just accept it for now. But this implies, of course, exactly what we wanted, because now it implies that f prime is an isomorphism. Right? So the isomorphism between the image and the geometric realization. So that is, in fact, the homeomorphism we want. Okay. So why do we do this? Well, the point is now we have an immediate corollary, which is that any two embeddings of the same graph will be homeomorphic. Right, because we just showed that any embedding will have an image that is homeomorphic to the geometric realization. So if I look at any two embeddings, as the image of any two embeddings of the same graph, then they're also going to be topologically equivalent. In pictures, or at least in diagrams first, that means I have a graph G. I take a geometric realization of G sitting in Rn, and if I took two different, let's say, planar embeddings into R2, let's call them F and G, that the image of F and the image of G are going to be homeomorphic. So two different drawings, at least, will still be topologically equivalent. So here's a nice example. If I took a graph like this, say it's just a pair of triangles sharing an edge like this, I might have another embedding of this same graph that looks like this. And I might even have another one. Let's do one like this. Let's say so these are three different embeddings of the same graph into the plane. And so the subsets of points that I hit here are all homeomorphic. Again, ignore the little gaps I use just to highlight where the vertices are. So this is a pretty strong statement. It tells us that, that we can look at the drawing of a graph, and any facts that we see, any properties we see that are topological, we know that those are going to be present in any drawing of the graph. Okay, so this is the first case where we really get clear information from the drawing. We know that if we draw it a certain way, and it's a proper drawing, it's an embedding of the graph, so no crossings, that all the topological information will be the same. There's certain things that we kind of already knew. For instance, like if you drew it with two pieces, right? Having two different connected components, we'll talk about connected components in topology soon, but having two pieces, two connected components, well, we know that any embedding is going to have two pieces. It's going to have two different connected components. They might be arranged differently. You can imagine a cycle and a cycle. They might be next to each other. One might be inside the other. But topologically, they're the same. They're still a continuous invertible map with a continuous inverse that maps between those two. Okay, so this is a nice, strong equivalence and gives us a whole class of embeddings of the graph, and that they all form the same equivalence class in homeomorphism. All right, so we'll talk a little bit more about some of these topological properties, in particular how to hide one graph inside another in the next video.